using the trapezoidal rule when you either have a function that is ridiculously impossible to integrate or you don't have a function at all. This is where the trapezoidal rule really comes in handy. So we have a table here listing several measurements gathered in an experiment. The experiment is completely irrelevant. You can put whatever you want in here, it doesn't matter. The X data is increasing by 0.25 each time. The Y data obviously is changing as well. So this is approximating, we are going to approximate an unknown continuous function using using the trapezoidal rule. So I'm just saying I'm going from 0 to 2, and my data goes from 0 to 2, whatever that is, time, I don't know, meters, years, something. Then, after we're done with that using the trapezoidal rule, we're going to use our graphing utility, so we'll get on our calculators and generate a third-degree model for the data. And then we'll integrate that data, or we'll integrate that polynomial over the interval from 0 to 2 and compare the result. What do you think we'll get? Like between the two. Will they be vastly different or will they be mostly similar? Probably mostly similar. Okay. So what we're going to do, just like with the bus project, is plot these. Okay? Now I'm not actually going to go to a spreadsheet and plot them, but I am going to make a little scatter plot here just so that we can kind of get an idea conceptually of what it is that we're doing with the trapezoidal rule. So each one of these time intervals is broken up into quarters of a whatever, quarters of a second, quarters of a year, something. So by 0.25. So I need to go from 0 to 2. So that means that's 1. So there's 0.5 and there's 0.25. So this is just a real quick sketch to help me realize what's going on. 1.5, 1.75. Okay. And then I'm in the 4s, I'm in the 5, 6, 7, 8. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. And then I'm just going to try to put these dots on here real quick. So the actual position of the dots, since this is just a sketch and I'm not really using it for purposes other than to try to picture what's going on here, this is the general idea of what my graph would look like if I was to like put it on Excel or something. So now that I have this down, I can start thinking about the trapezoidal rule. This 0, 0 goes with 4.32, it's right here. And then the 0.25 and so on. So I want to use the trapezoidal rule to approximate, which means I'm going to wind up drawing a bunch of trapezoids in here. So we'll come up to both of those points and then draw a little line over. Up to there, draw a little line over, and so on. So that's the idea. Okay? Now, the trapezoidal rule says what? We do? That's not n. That's delta x. This distance right here, in between each, is constant. It's 0.25 each time. If it wasn't constant, then what we would do is just apply the delta x to each individual rectangle. Like, it's possible that I could give you a problem that has varying widths on these rectangles. And then all you need to do is figure out how wide each, not rectangle, but trapezoid is, and then apply the delta x to each, instead of taking the delta x as a whole and multiplying it in. So I'm just looking for what the formula for the trapezoidal rule is. So the integral of the function dx equals, so from a to b here, b minus a over 2n f of x sub 0 sub n minus 1 plus, there you go. So let's remember what these little parts are. The b minus a over n is what?
1/2.
That's your delta x. And then the 2 underneath is actually the 1/2 times delta x. Each of these guys is there for a reason. This guy is just f of x sub 0 because it's only getting used once. That base of that trapezoid only gets used once. The rest of these, with the exception of the last one, have bases that get used twice. So this one gets used on this trapezoid, and that's why we see the 2f at x sub 1. And the same thing is true for all these all the way across until we get to that last one. That last trapezoid, this piece gets used twice, but this piece only gets used once. And that's why that last piece only has just f of x sub n. Okay, so we should start identifying parts in our problem here. We know that we need the 1/2. We know that we need b minus a over n, which just gives us delta x, but we already know delta x. What is it? Okay, so that is delta x equals 0.25. What else do we need to know? Before that even. No? We have b minus a over n. Do we need to know the number of trapezoids that we have? We already know delta x. But how many trapezoids do we have? This is worth noting. How many trapezoids would we have here? One, two, three, four, 5, 6, 7, 8, 9 points of data. But that makes a trapezoid. That makes one. That makes one. That makes one. That makes one. Another one here. Another one here. And then that one. 1, 2, 3, 4, 5, 6, 7, 8 total. You could. If you wanted to plug in n, like maybe you don't know, from 0 to 2, we'd do 2 minus 0 divided by, we're forming 8 trapezoids. 2 divided by 8 is 0.25. So that's where the 0.25 is coming from. All right, so I just wanted to point that out. We have 9 data points, but that means that there's 8 trapezoids. Okay, so we have 1/2 times delta x. So that is 1/2 times 1/4, which is 1/8. So it's going to be the integral from 0 to 2 of the function, which we will never know, equals 1/8 yeah, that's kind of in the way, so let me get rid of that. Okay. Plus 2 times 6.14 plus 2 times 7.25. Yeah, there's no way around this. You're going to need a calculator. Plus 2 times 7.64 plus 2 times 8.08 plus what? Just 8.14. When you multiply all that out, you get the integral from 0 to 2 of f of x dx equals, and you'll have an answer. So 12.51? 52? Okay. 12.52. So that would be the area under the curve that you just found, for whatever reason. In this experiment, apparently you wanted to find out what the area under the curve was. Maybe this is the bus as it's traveling down the road. But this is how you would do it mathematically. Okay? Now in Excel, if you had a whole string of data, like maybe 100 data points, it is easy in Excel to come up with a way to represent this formula so that it gives you the answer in the end. That's easy to do. Yeah, so yeah, definitely a spreadsheet is nice. So what I want to do here now is the second part. Using a graphing utility, find the third degree model. So we're going to make a scatter plot and force it to give us the third degree polynomial. If you don't remember how to do that, bring up your calculator from the home screen. down to the green icon, the spreadsheet icon. You want to label the top something. We don't have variables here, so I'm just going to call it triple X and triple Y. The calculator will probably freak out if you don't call it more than just X. And then enter in that data. So once all the data is entered in, you go back to the home screen, and the purple icon, Data and Statistics, brings up your scatter plot. You need to organize your data. Go down to the x-axis, your x variable, slide over to the y-axis, pick your y variable. Oh, wow. So there's your data, and the directions tell me to fit a third-degree model to this data. So to do that, you press Menu, and then Analyze, and then Regression is option 6. And we wanted a third degree, that would be a cubic. So there's my polynomial right there. Now we want to write that down, and I'm never going to remember it, so. Alright, so the polynomial is down here at the bottom. And now what I'm going to do is go back to the home screen and insert a calculator into this document. And now I can evaluate that integral. I don't need to actually integrate it. If this was an AP exam, then yes, I would want to show my attempt at integration on this, which actually wouldn't be that difficult, so let me go ahead and do that. If I integrate this thing, then I'd have the integral of my function, which I don't want to use y probably. I should probably call it f of x. So if I integrate my function from 0 to 2, then what I can do is go ahead and integrate that as I go. Since this is a polynomial, I know that my exponents are going to increase by 1 each time. So then I'll have negative 1 point. Is that 1 point? Okay. When I split up, I think my dots disappear sometimes. So 1.37266 x to the 4th over 4. Good enough. Plus 4.00924 x to the 3rd over 3 minus 0.620154 x squared over 2 plus 4.28444 x over 1, technically, right? Now all of that is being evaluated from 0 to 2. So if I don't have a calculator sitting in front of me, which I don't know why I wouldn't, considering I just came up with this using a calculator, then I would continue showing work. I believe that on the AP exam, this is going to be good enough. You show me that you know what you're doing, you show me the process for which you're doing it, and then you use your calculator to write down the answer. Don't just write down the answer. So now in the calculator, we're going to go ahead and enter all this in from here, using the calculator template for integration. So now in the calculator, we're going to go to the little template button, not the 9, the template button, and then select the integral one, which is down towards the bottom right there. And it brings up your integral. And we're going from 0 to 2. Now I can type in my polynomial and then dx. Can you copy it? So anyways, I'm going to have to enter it in, so we'll just enter it in. So once I get done entering all that stuff in and I press enter, I wind up with 12.52. 12.53. What did we get? We got like basically the same thing. So if you go back to the scatter plot that we created, which is right there, you can notice that the data matches up extremely well with the polynomial that we gave it. So it's a little off here, a little off here, a little off here. That's fine. So conveniently, the data matched up with a third degree polynomial really well, which is why we wound up with a really close polynomial approximation from the trapezoidal rule. But notice that the trapezoidal rule, without that polynomial, got the job done just as easily. So technically, I mean, it's not exact, but this polynomial models the data extremely well, and the trapezoidal rule came up with an answer that is incredibly close to that pretty good polynomial for the data that we're given. So the trapezoidal rule definitely works. It works very well. So that's why we prefer to use that one, and that's why that one is usually the one that's on the AP exam, because it's by far the best. It's kind of following a primitive sort of method, but as delta x gets smaller and smaller, the trapezoidal rule gets infinitely better.